So, simple derivative rule here. We know the first derivative already, so the second derivative is just taking the derivative again, bring the 3 out in front, subtract 1 from the exponent. The inside function is x minus 3, so we don't have to do a chain rule, because the derivative of x minus 3 would just be 1. So now we have f prime of 3 is equal to 0, and f double prime of 3 is also equal to 0. So now we're going to think back to our original function. On our original function, it has an x-coordinate of 3. And we want to explain why this isn't an inflection point. So a little bit of a reminder, an inflection point, two things have to happen. One, the second derivative has to be equal to 0 at that point. But what we mentioned last class is that's not enough to show something's an inflection point. As in this case, where the second derivative is equal to 0, but we're going to show that it's not an inflection point. Besides just being equal to 0, we have to show that it changes sign at that point. So a couple of things. Two sign diagrams are going to be very useful when we do all of our graphing using derivatives. One sign diagram comes from your first derivative. So from our first derivative, which is already up there, you can see that it's equal to 0 when x is 3. So if I made a number line and put 3 on here for my first derivative, what happens before 3 for my first derivative? Well, if I plugged in 0, can you see you would get negative 27? So the first derivative is less than 0, negative in this section, meaning your original graph was decreasing. And if you plug something in larger than 3, we find out that this is positive, meaning that f prime of x is greater than 0 at that point. So one sign diagram that we're going to use is find out where your first derivative is equal to 0, and that will tell where your initial function is increasing or decreasing. From that first derivative, we can tell that at 3, we have a minimum. From the second derivative, we'll also draw a number line where it's equal to 0. When we go to graph this, we know that it's equal to 0 at 3, but now when you plug in values into your second derivative, and our second derivative is 3x minus 3 squared. Squaring makes anything positive. Can you see that this is always going to be positive? And according to this then, your function is always going to be concave up. So we can use those number lines to check about concavity and about where a function is increasing or decreasing. But since the first derivative changes sign at that, it can't be an inflection point. It has to be a local minimum. So that would be one reason, one way that you could explain that it's not a point of inflection. Or, just like we did before, you can show that even though it's equal to 0 at 3, it's concave up both ways, on both sides, so it doesn't change concavity, and that makes it not an inflection point. So here is a question just asking about concave up, concave down, and inflection points. So if you have your original function, you're going to need to find your derivative and then find your second derivative, because your second derivative is going to tell you where things are concave up and concave down. So this is a simple, straightforward derivative, and then we get our second derivative is just 6. That means your second derivative is always positive because it's equal to 6. So this whole thing will be concave up over its entire range, which if you think about the original graph, that's a parabola. Can you see that a parabola opening up is always going to be concave up? It has no inflection points as a result, because the only way you can have an inflection point is if your second derivative is equal to 0 and it changes concavity at that point. Or your first derivative doesn't switch from going increasing to decreasing to make it a minimum or a maximum. Here's our next one. We'll do one more together, then I'll give you a chance to try a couple of them. So again, we're trying to find inflection points and say where something is concave up or concave down, and then I'll have a sketch from our graphing calculator to show us what's happening. So in this case, negative 2/3 x cubed minus 4x squared plus 10x. We find our first derivative, and then once we have our first derivative, we can find our second derivative. In this case, it can equal 0 when x is negative 2. If we draw our number line, let's just do this together. If we draw our number line and label negative 2 on that number line, if we want to find out if our second derivative is positive or negative, to find out concavity, we are going to plug in values into our second derivative. So when I plug in something less than negative 2, say negative 3, into my second derivative, can you see that you're going to get a positive number? And if this is a positive number, this section will be concave up. And if you plug in something larger than negative 2 into your second derivative, say 0. Negative 4 times 0 minus 8 is negative 8. This section is going to be negative, so you'll know that entire section will be concave down. So for this one, it's concave up from negative infinity to negative 2, and then concave down after negative 2. Here's a graph from our graphing calculator. The blue section you can see is concave up, and the red section is concave down. If you want to find that inflection point, you would have to plug negative 2 into your original function. Remember, anytime we want to find an actual point on our original graph, we have to plug those x values into our original function to find it. That's the same is true if you find maximum and minimums, and the same is true if you're finding points of inflection. To find actual points on your graph, you plug them into your original equation. To find out concave up and concave down, that's where you would plug it into your second derivative. If you were graphing this by hand right from the beginning, you would do your first derivative. You would make that equal to 0 and solve. Does this one factor nice? If I take out the negative 2, x squared plus 4x minus 5, it does factor nice at x equals negative 5 and x equals 1. So if you were graphing this completely by hand, which we will do coming up, you would do your first derivative. You would find out where your first derivative is equal to 0. You would draw your sign diagram with negative 5 and 1 on there, plug in values, and in this case you would find out this is negative, so it's decreasing. then positive, increasing, then negative, decreasing. If you wanted to find out what the y-coordinate when x is negative 5, that's going to be that minimum right there. You'd plug that negative 5 into your original function and find the value. If you wanted to find out what this red point is up here, that's your maximum. That's when x is 1. Plug that into your original function and find that value. So then you would have this value, our maximum, our minimum, and our inflection point. From your first diagram, you would know that it's decreasing, then increasing, then decreasing. And from your second sign diagram with concavity, you would know this part is concave up, this part is concave down. And you'd be able to draw a pretty good sketch of your graph because you would know maximums, minimums, where it's increasing and decreasing, and what the concavity is. So, a couple for you to try. Scroll down a bit. So while you're working on that one, if you want to check certain things, you can. So a couple things to discuss in this one. First of all, notice that factoring things can really help you simplify. So once I've taken the second derivative, again, I notice that there is a 2e to the x in all of the terms. So you can factor that out in front. You could have even seen that 2e to the x in the two terms when it's up here as well and factored it out at that point if you had wanted to. And then when you set that equal to 0, it's important to understand e to the x never equals 0. It's an exponential graph. It has an asymptote at y equals 0. It never equals 0. So the only place that we can have our function equal to 0 is in the second set of brackets for 2 plus x. That's going to equal 0 at negative 2. So we're going to be concave down from negative infinity to negative 2, and then concave up from negative 2 to infinity. Here's what the graph looks like. The red section is the concave down section. The blue section is concave up. This graph has an asymptote as x goes to negative infinity. It gets close to 0 but never goes above 0. So at the bottom of the page there, you have a place where you can look in your textbook for some more practice questions. Unfortunately, with IAs, other subjects, and everything else, when was the last time you opened up your textbook to look at any of the practice questions? Last weekend? Okay, that's not too bad. Last year isn't too bad if you think it was only like a month ago. But I know, it gets busy. I will tell you that if you work through all three of these reviews, I know it's a lot of stuff, but you will be well prepared for your midterm.